started. Okay, so using what are called the T procedures. And basically, you use these when the standard deviation of the population is unknown. Okay? And if you think about it, in most of the problems we've looked at so far, and all the problems we've looked at so far, we knew what sigma was because it was told to us in the problem. The standard deviation of the population was given to us and so forth. And we've hinted at the idea that that could be a little silly sometimes to assume, but okay. So what do we do? First off, when sigma is unknown, we start by doing the following. We estimate sigma with S of x, where S of x is the standard deviation of our particular sample. Okay? If you think about it, when you have an x bar, when you do a sample of some sort out of a population, you can get a standard deviation from that particular sample. And what I'm saying is, if we don't know sigma, we're going to use that S of x to estimate it. Okay? All right. So if we think about hypothesis tests, something we required in the past was we required to know what sigma of x bar was, the standard deviation of the sampling distribution. And we said that that was always equal to the standard deviation of the population divided by the square root of the sample size. So obviously we can't use that anymore, right? Because we don't know S of x. This, again, just so we're clear, that's the part that's unknown. And when that's unknown, that's when you have to use the T procedures. So instead, we use this. S of x bar equals S of x over square root of n. This is sometimes referred to as the standard error. Okay? And here's what else changes. The distribution of x bar is modeled by something called the T distribution, which changes according to n. So n is your sample size, and what I'm telling you is that this is not a normal distribution anymore. It's something called a T distribution, and the T distribution changes when n changes. Okay? That's what this is about. So I'll draw a picture for you, and you'll get a sense of it. Okay? So here is the normal distribution. Okay, not a great picture, but you'll have to tolerate it. That's the normal distribution. Okay? And the T distribution looks like this. It's a little bit wider and not quite as tall. So that's the T distribution. Now, I did tell you that the T distribution would change according to how big the sample size was. Okay? So if you look at charts for T distributions, they'll have these two letters next to it, df. And df stands for degrees of freedom. And in the case of a T distribution, or, well, we'll just simple this. In the case of a one sample test, the degrees of freedom is equal to n minus 1, your sample size minus 1. Okay? So what you'll notice is in this picture, this red distribution I've drawn is not a very close fit to the normal distribution. And the reason that is because the degrees of freedom here are low. It's probably degrees of freedom 1 or 2. Okay? But as the degrees of freedom increases, as df goes up, then the T distribution gets closer to the normal distribution. So here's what I mean. What I mean is, let's say you had a bigger sample size, and then your degrees of freedom would go up. So if the sample size were maybe 5, then degrees of freedom would be 4, you might get a t-distribution that looks like this. So the green one is a t-distribution with degrees of freedom equal to, I don't know, 4 in this case. Okay, because it was n minus 1. I was saying, hey, pretend n was 5. And then lastly, if you let n get really large, then what you start to notice is that the t-distribution would be really, really close to the normal distribution. Something like this. Not perfect picture, but you'll live with it. So that might be the t-distribution for degrees of freedom equal to, 35 or something like that. And you'll notice how these curves are very close together. So if you look at Table B, you'll notice along the bottom, here's what it looks like. So let's say you go to a confidence level of 95%. And if you look above it, you're going to see a familiar number, 1.960. And that's the number, that's the Z star we used in our confidence intervals for 95%. But if you look over to the left, you'll see an infinity. Okay? And that column over on the left is titled DF, or degrees of freedom. Okay? So, and what you'll notice is as the degrees of freedom goes down, so like above it is 1,000, you'll see that this is 1.962. And then way above that, at some point, you'll find the number 40. And if you look across for the 40 at 95%, you'll see it looks like 2.021. Okay? So these numbers up here, while this number on the bottom is called a Z star, all of these numbers in the column are called T stars. Okay? So that's what's going to change now in our confidence intervals. Instead of having Z stars, there's going to be T stars. What you'll notice is this T star is bigger than 1.96. So you might think about why that's true. So let's think about this for a second. So here's the normal distribution. And basically, the meaning of these two numbers is as follows. If you want to catch the middle 95% of area, if you want that to be how much area you catch, you need to go from Z equals negative 1.96 to Z equals positive 1.96. That's why this is called Z star. It's the perfect Z score that will catch the middle 95% of area. Okay? So let's think about a t-distribution for a moment with degrees of freedom equal to 40. Now, this is not going to be perfect, but the picture I'm trying to draw here would be a little flatter and a little wider. That's very exaggerated, but it's a little flatter and a little wider than the curve up here. So we need to go out a little bit further. We need to go to t equals negative 2.021 to t equals positive 2.021 in order to catch an area of 0.95. And that sort of makes sense because this new curve is shorter and wider. So since it's shorter and wider, we have to go further out to the left and right to catch 95% of area. If you look back at that t-chart, if you look for really low degrees of freedom, like look at degrees of freedom 2, for example, and you go across and you look for the t star there, the t star is 4.303. So you have to go much further out if you have a low degrees of freedom. And that makes sense because if degrees of freedom are really low, then that means your t distribution would be even wider and flatter than this red one. It might be something like this. So you need to go much further out, t equals 4.303, down here to t equals negative 4.303 in order to catch that middle 95% of area. So let's continue. All right, so what do confidence intervals look like? Surprisingly similar. X bar plus or minus t star s of x over rad n. So you notice it looks just like the old confidence interval, except instead of z star, we have t star. And instead of sigma of x, we have s of x. Okay? All right, so, and let's be careful here. Remember, t star is always calculated using n minus 1 degrees of freedom. Now, you can't use a confidence interval unless you check certain conditions. So we need to talk about those. All right? So when is it safe to use the t procedures. Okay? All right, so couple like conditions. So let's pretend n is less than 15. Okay, so if you have a really small sample size, then you can use the t procedures, okay, if the data are close to normal. Okay, so how do you check that? You use like box and whisker plots, and you hope that they're nice and symmetric. And then you also need to check the normal probability plot, the NPP, and make sure that that thing is pretty linear. All right, that's what you want. So as long as there's no strong skewness, there could be no strong skewness or outliers, along with a linear NPP, then you are safe to use the C procedures in the case where n is less than 15. So this is sort of broken into cases. You have to worry about that. Okay? All right, but you have to have both of these, and you have to have some good reason to suspect that that is normal. Okay, moving along. What if n is between 15 and, let's say, about 30? Okay, somewhere in there. Then here again, same conditions. No strong skewness or outliers. You can have some moderate skewness, like, you know, if you draw your box and whisker plot, and maybe it's got a long tail on one side and a short tail on the other. That would be okay. Your normal probability plot doesn't have to be perfect here. Back in the case of n equals less than 15, I should even go a little bit further here. I should say no strong or even moderate skewness. You really don't want any skewness at all in the case where n is less than 15. Okay? But if you go between 15 and 20, you can tolerate a little bit of skewness. Okay? That's that. And then lastly, if once n is greater than or equal to 30, then you could just use the t procedures. All right? That's what you get. That's not a central limit theorem statement. You could just use the t procedures. We can't use central limit theorem because sigma's unknown. Central limit theorem requires you know the standard deviation of the population, and we don't know it here. So let's practice using the t chart for a minute. All right, so let's pretend we had a confidence level of 95%, and we had n equals 10. The question is what t star would go with that. Okay? So you go to that 95% column in your table. You'll look up if n is 10. That tells us that the degrees of freedom, which is always n minus 1, is equal to 9. So we go to the 9th row, go across to 95%, and I am getting 2.262. Let's try another one. How about 99%? Okay. And you had n equals 20. Let's see if we can figure out the t star that goes with that. So the degrees of freedom here is 19. You look in the 19th row, and you look at 99% on the bottom, and you get 2.861 as your t star. Okay. How about this? An 80% confidence level, n is equal to 7. So t star in this case is 1.440. Let's actually try and do a confidence interval. All right. So this is problem 10.39. All right. So here in this question, they give us some information. They give us a list of numbers that starts out as 28, 32, 25, 34, and so forth. It goes all the way down to a number 21. And they're asking us to find a 95% confidence interval. Okay. So let's get our calculator going. All right. So our confidence intervals look like this. X bar plus or minus t star S of x over the square root of n. Okay? Don't forget, let's just remember some terminology. That thing is called the standard error. The whole thing altogether is called the margin of error. Okay? And S of x, this S of x up here, this is the standard deviation from our particular sample. So here's all the data in the calculator. There it is. And what we're going to do is we're going to do stat, calculate, one variable statistics, in my case, list 2. All right, we hit enter. We get an x bar of 25.42, so we're going to go write that down. So 25.421 plus or minus. Now t star I don't know yet. Square root of n I don't know yet. And s of x I don't know yet. So let's go see what we got. Well, n's 38. That's good. That's a nice big sample size. So we know by our rules it's safe to use the t procedures. So n is 38. S of x is given to us. It's 7.475. 7.475. And then lastly, t star, well, we want a 95% confidence interval and a degrees of freedom equal to 37. Okay? Now, if you go to the t-chart that you have, you're going to notice the following. There's no degrees of freedom at 37. You'll see a degrees of freedom of 40 and a degrees of freedom of 30. And if you look at 95%, you look at those two numbers, I'm getting 2.021 and 2.042. 2.021 and 2.042. In this case, you can just round to the closest one. You'll probably be okay. Some books will tell you, or some people will tell you, always round down to the lower degrees of freedom to play it safe. It doesn't really matter. So here we go. We're going to 2.021. And this thing here is our confidence interval. And you know how to type that in and figure it out. I should point out that your calculator could do a confidence interval for you. Watch this. So back on the calculator, if you do stat and you go over to tests. Now let's think about this. A z-test is done if you know the standard deviation of the population. We don't know that. T-test we'll do in a little while. We haven't done any two-sample stuff yet. There's a one proportion z-test. We've already done those. There's a z-interval, which we can't use because you require sigma. And look at that, the t-interval. So there it is, right? So I hit enter. And the information from the last one variable statistics you did is already in there, which is really pretty neat. In other words, when you do one variable stats, the calculator automatically populates this information into the t-interval and z-interval stuff. So I'm going to go down to the conf level, change that to 0.95, and hit calculate. And this interval we get, 22.964 to 27.878. That's what we would have gotten had we taken the time to actually type that thing out. So we can say we're 95% confident that the interval from 22.964 to 27.878 captured the true mean of this particular population.